The recording. So, hi, folks. Hi, what relatively few folks we have today. We've got 3 students, actually, nope, 2 people enrolled in the class, 1 auditor, 2 TAs. That's what we've got in the room today. I will try not to take it personally. I know this is the point in the semester where everything is getting crunched and competing priorities happen, but I understand. That's why we're recording, so that you can catch up later if you're not able to join us for the live show. So we are working on homework 4 right now, right, folks? Had some visitors in office hours. I wanted to tell you a little bit about where this homework came from and then give you some pointers on how to approach the monster simple slopes section 2. So this homework is a true story, okay? My son is, as I've discussed before, he'll eat only like 5 different things on Earth, and he's trying to die of malnutrition. He never ever asks for food, and he treats it as a problem whenever we try to feed him. I'm not hungry. You need to eat breakfast. Why? Because this is when we eat breakfast. I'm not hungry. Like, it's every day is this, for every meal. Like, he never asks for snacks. He never asks for food, okay? And we were concerned that he was going to be malnourished, and one of his teachers suggested a therapy program that is, we called it Food School. And he went to about 3 sessions, and then the pandemic hit. And we weren't able to take him someplace without a mask on where he'd be eating in front of perfect strangers in a tiny little room. So we never did finish the Food School program, but it is a real thing. So they focused on getting kids to not freak out about new foods by just like, are you willing to look at it? Okay, are you willing to poke it with a fork? Are you willing to touch it with your hand? Are you willing to smell it? And like there's these, each time, and there's like stickers and like a reward system that's built into this, so it is a real thing. Unfortunately for us, though, the covariates in this story are also real. So older siblings versus younger siblings, that's not an issue because he is an only child most of the time. But whether or not your parents work full-time is the other part of the story, because we were told that to help him with this problem of not wanting to eat and being afraid of food, that we needed to constantly make new foods for him and give them a chance to try. And I don't know about you, but if you're busy and you're hungry and you're tired, making a buffet of choices for him to like turn his nose up at is not going to be the first thing I do. So my hypothesis is that Food School might be less effective if the parents are not willing to do the part that happens at home. So it is based on a true story. From your perspective, this is a count example. So the outcome being predicted goes with example 3 as the code that you should be referring to, the count of number of new foods tried, including 0 as a possible alternative. That's what my son would do. And so we are using Poisson and negative binomial models. And the tricky part in terms of the coding of the predictor is to categorize Food School attendance into 2 different variables. So this conceptually is like a hurdle model, but on the predictor side. I wanted to differentiate the effect of being in the program at all from the effect of how many sessions you attended as more of like an exposure or what's the therapy term for it? Like, is that right?
Exposure.
Exposure works? Okay, great. I'm a clinical psychologist today. Outstanding.
Like you have a degree in psychology.
I do have a degree in psychology. And actually, more technically, I have a degree in philosophy, right? And that is just crazy to me because I can't do philosophy or psychology anymore, but that's what it is. But anyway, so you are supposed to create one new predictor that covers the difference between 0 sessions and any more than that. So that would be a dummy code. And then a second predictor for the number of Food School sessions past 1. So I've seen a couple versions of the codes from folks where they're literally saying like, if it was 1, make it 0. If it was 2, make it 1. If it was 3, make it 2. And that works. But a faster way to do that is to take the original variable and subtract 1. And that will turn it into the new variable. So if the original variable was greater than 0, then you can just take the original 1 minus 1 and create the new one. And you'll note, please refer to lecture 1, slide 15 for hints on how to do this. There is a slide that I put in as an Easter egg at the beginning of this semester because I knew I was going to have this homework. So you can refer to that for an example of what the code would look like for this. So the first section is an empty model where you are comparing distribution fit for Poisson versus negative binomial. And then in section 2, there is the big model. So the questions then, we want to focus on whether the child has participated at all and how many sessions, their exposure, whether they have an older sibling, whether they have a younger sibling, whether their parents both work full-time. Those latter 3 are dummy-coded variables. And then also examine fixed effects for the extent to which the success of food school for both any participation and amount depends on whether their parents work full-time. Okay, so that is more of a layperson's way of saying this, except for the fixed effects part. How would I translate this idea? Depends on. What is that code for? If I want to know if the effect of food school depends on whether your parents work full-time, what am I asking for? What kind of addition to the model? Zoomers, you can play along. Depends on. Moderator. Yeah, interaction terms. To what extent does the success of food school, so the idea of how effective this is being operationalized as a slope, relating the food school predictors to number of foods tried, whether that slope depends on, varies by, or is moderated by full-time work. Thank you. And the TAs are both in the Zoom room, by the way, if anyone wants to ask them questions. So I was helping folks in office hours yesterday, and I thought, well, why don't I just do this in class? So I wrote out an example for what the model would look like. So we are, and this is the fast way of typing, so forgive me for not using proper notation, but this is, this is good enough for present purposes. So I have an intercept, of course. I have the effect of having a younger sibling, having an older sibling, and then what I would call main effect of whether your parents both work full-time. The two food school variables, so I've named these FS1 and FS2. And then these 2 latter terms are the moderations, the interaction terms. So in your homework, there is a question, number 19. Enter 1 if you are ready to compute simple slopes for the moderation of food school effectiveness by full-time work. Now, I did that for 2 reasons. The real reason is because I had another question there that I realized was getting different answers across software, and I didn't want to deal with that. And to take that question out would require reordering a million pieces of code manually, and I didn't want to do that. So I needed to put in a placeholder question. But I decided to make it this question so that you would be primed as to what the following questions were asking you for. Now, these questions are long, but part of the reason of why I'm doing it this way is to try and help you recognize how ideas, in terms of research questions, map onto model parameters. So the hardest part about all of these is going to be, what is she asking me for? Like that. Once you get that, you're home free. So for instance, enter the difference in predicted log count for children who have or have not attended food school. And then I put in a comma, which technically isn't needed, but I put it in there to help you parse the sentence. So this wording right here, the difference in predicted log count for children who have or have not attended food school. What am I asking for? What is the model parameter that goes with that idea? The difference in y for a 1 unit difference in x is what these words, that's the template that underlies these words. So what am I asking for? That part in particular.
So participation, I mean, if you are coded your new variable as 0 and only 0 and 1 for the attendance for the food school, so that variable, that specific variable would be the main interest?
Yes, the slope. So this question is asking about the slope of the first food school variable, as you said, that differentiates people who never were in it or who were in it for one or more sessions. So the difference in predicted log count, the difference in y, for a 1-unit difference in x. I'm asking for the slope of food school 1. Okay, so that is the thing that I need. So in terms of the rules of how to compute a simple slope, 3-step process, right? Go into the equation, find all of the terms that have the variable the slope is 4. Okay, so let's go into my model here. So if I'm interested in the effect of food school 1, that's just what I want. I want the slope that describes the effect of this predictor. Then I need to go figure out what my ingredients are. So do I need beta 0? Do I need beta 1, 2, or 3? I do not, because they don't have anything to do with food school. And food school is the predictor that the slope is 4. That's what I'm trying to find. Now, I've had a few conversations where people try to put in something related to work because the question said, I want it for somebody who doesn't work full-time. Right idea, but the wrong term. I don't need this because this has nothing to do with the effect of food school. It's not relevant. Do I need beta 4? Yes, I do. Let's take that down here. Do I need beta 5?
No.
Yeah, this is the tricky part. No, because what I want is the difference between people who are in the program or not. So the second one is keeping track of differences among the within the program people. So we don't need this one. Do I need this one? Beta 6. Yes, I do, because it has food school in it, the first variable that I care about. Do I need the last one here? Beta 7. I do not. Okay, so that's step 1. So you would be starting to write a LINCOM statement in Stata, a GLHT statement in R, an estimate statement in SAS. Any of those will do it. Step 2, factor out the variable the slope is 4. Okay. So that means get rid of that, get rid of that. These are your ingredients to form the simple slope. So then now we can go with the specific case. If I want to know what the slope is for somebody whose parents do not work full-time, work is 0, what do I put here? Yeah. And if I want to know what the slope is for somebody whose parents do work full-time, put 1 here. Okay, you know what the next question is going to be? Let me double check to make sure I'm right. Yeah. So here's 20. We just did 21. Now 22. Enter the difference in the slope for any food school between children whose parents do not versus do work full-time. What am I asking for? Like, I don't know, but I know that if I want the difference in the 2 slopes that you just found, I've got the ingredients. So here's one of the slopes. Here's the other. If I want them in the right order, to go with the question, it needs to be the second one minus the first. Difference in the slope equals. What's beta 4 minus beta 4? Yeah, I'm making a minus sign there. There we go. So beta 4 drops out, right? What is beta 6 times 1 minus beta 6 times 0? Beta 6. So I'll ask the question again. What am I asking for when I say the difference in the slope? Beta 6 is the interaction term. Interaction terms tell you about differences between slopes. So in terms of what I would have to write for code to answer this question, it would only be the linear combination where I need to add 2 things together. I need to ask for that as a new parameter. And I could get my calculator out and get the answer right. but my calculator isn't going to give me the right standard error and the right p-value. Not unless I do more complicated formulas that involve the asymptotic covariance matrix, and I don't need you to memorize that shit. I need you to learn how to use the code to do it. Because the code will always work. The formulas have to be adjusted based on the model. Okay, how are we doing with this? I will post this on the website, okay? That way no one has any unfair advantages. Yeah. Well, it's not like I can keep it a secret, right? Because then you can just like pause the YouTube video, but I figure if people are going to do that, I may as well just post the document. It's fine. If you go through the rest of the questions, they will have a similar structure. Find something, find the difference. Find something, find something, find something, find something, find the difference. So the first thing is always figure out what the slope is the question is asking about, and then figure out which terms you need to moderate it. The predicted counts, you can do those using margins in Stata. You can do those using there's a function called prediction and a package called prediction in R. And I have examples of what that looks like in example 3. Okay. Any other questions on homework so far? Zoomers, feeling better with this? Okay, then I will let that go. Model scale and data scale. So those are terms that have to deal with what the scale of the outcome is with respect to the link function. So model scale would be like things like the predicted logit, the predicted probit, the predicted log of the expected count. That's model scale. It's like what does the link function say y should be? Data scale is then inverse link back down to what the predicted mean is. So probabilities and expected counts, unlogged expected counts. And yes, I have a disclaimer in the instructions that I got tired of typing expected into every single sentence, and so it's just count or log count. So yes, those questions about model scale versus data scale, 2 of them are internally inconsistent. And I'm looking for you to recognize that and rule out those 2 and then decide which one it should be after that. All right, didn't want that, I wanted this one. Okay, in the meantime, we finished counts. We get to talk about other kinds of not normal outcomes, including proportions and continue-ish things. So that's where we were last time on Zoom. Should we go back over some of this before we dive back in? I should not assume that you have perfect and complete recall of every word I've ever said. Does that sound fair? Yeah. I don't even have perfect and complete recall of every word I said. Okay, the big one, proportions. That's what we've been talking about here. Make this slide bigger. This is slide 4 of lecture 4. So proportions, things like accuracy, percent correct, any of those sorts of things, as well as scale scores that don't have boundaries of 0 or 1, but have boundaries at some other point. So for instance, if I'm going to borrow Vladimir's example from a simulation he's designing, he has a fictitious outcome that has 10 questions, and each has choice from 1 to 5. Does that sound right? Something like that? And so then the logical range of that scale, if you answered 1 to everything, you would have a score of 10. And if you answered 5 to everything, you'd have a score of 50. So it's still kind of the same idea because you have these upper and lower boundaries that your outcome should not be predicted past. So you can do a conversion to take any scale score and put it into a 0-1 metric with this formula here to make this work. But we are back to logits or probits, doesn't matter, because these outcomes have 2 boundaries, a lower and an upper. Logs are for outcomes that are bounded on the lower end only. And the tricky part with proportions is that what the model is predicting directly is the probability of a success, is the language that is often used for this, or getting a correct answer for any question any trial, any item, whatever noun you want to use to describe that. And then we multiply that by the number of possible trials, and then that's the mean. So the model is predicting in a roundabout sort of way number correct, but it's parameterized to give you proportion correct. The probability of any one trial correct is the proportion correct on your outcome as the mean. I know that's confusing, but it is working directly to give you what you can interpret as the same idea as the probability of a 1. It's the proportion of 1s out of the possible number of trials in this case. So we're predicting the log of the probability of any one trial, any one item being correct, divided by the probability of it being incorrect. So we're back to the same idea of logits, or we could use probits. So then data scale would give us the predicted proportion correct, probability of any one trial being correct, e to the logit over 1 plus e to the logit. Since we're back in logis, we're back in odds ratios for effect sizes as well. So the link on this is not the tricky part. The tricky part is trying to figure out what kind of distribution you have. So we started looking at some choices for that. Binomial looks like this. Here's a picture I stole from Wikipedia. Binomial has only one parameter to it to be estimated, p, the same as for binary, and you know already how many trials you have. So that's not, n is not an estimated thing. That's just the number of chances, essentially. So the mean is the number of chances times the probability of any one being correct. That works out to be the number correct, like the predicted number correct. Variance is determined by the mean. So in these distributions, we are assuming we know what the variance is if we know what the predicted mean is, but that's not likely to be the case. So in the example that we started, for instance, here's the picture. This is proportion correct on a test of grammatical understanding in 3rd graders, where most of the kids can do this by now. So we have this big ceiling effect where everybody's getting 100%, but not everybody. The rest of the distribution has this much longer tail, negatively skewed, than what a binomial model would predict. A binomial model doesn't have a tail as much. Like if you look at the green here, that would be the analog. This is a probability of 0.9. In the mean of this is 0.92 for accuracy. So this is what the data actually look like. So this is the idea of over-dispersion, the same thing that we had in count data. When there's more variance than what the model predicts, you can end up with too small standard errors and too small p-values. So we'll look at distribution fit to try to figure that out. Okay. Does that ring a bell? Maybe a little bit? Okay. So in this example, we're going to have only 2 predictors, a grouping variable as to whether the child has been diagnosed with specific language impairment, which is a condition of otherwise typical development, but our kids just for whatever reason grammar trips them up and they have a harder time learning it. And any language study involving young children needs to control for mother's education. It's just a rule. Not fathers, not grandmothers, not grandfathers, not any of that, just, mothers. It's my fault. And in this data set, I did not actually have the original number of items correct. I only had the proportion correct. So I had to reverse engineer that. So I'm building a variable that is incorrect out of the proportion times I gave it 100 trials and rounding it to the nearest. So then I have, like, for instance, somebody who got an accuracy of 0.88, they now have 88 trials correct out of 100. Did the same thing in R to build that. And then we are using GLM within Stata, as well as in R, VGLM. So we're back to that same package we used for ordinal data and nominal data. So first things first, trying to figure out what the model is doing, right? That's always first, particularly with these models. So I am fitting an empty model with a binomial distribution and a logit link in Stata, and so that's what the code is asking. Note that Stata needs to know number correct is the outcome, but it needs to know out of how many. to fit a binomial model. So it has the ingredients that it needs to build accuracy, essentially. In R, it wants the number correct and it wants the number incorrect instead of the number of trials. And it will add those together to come up with the total and build accuracy. So a little bit of differences across packages. In SAS, as I remember, it is this way. It is number correct and total. And you literally write that as like a fraction where the outcome would go. So what this model gives back has one parameter. Here's my mean. The mean is 2.45. Does that mean that on average people get 2.5 trials correct? If you didn't know the data, that might seem like a reasonable interpretation. What metric is this in? Logits. Is this model scale or data scale? Model scale, yes. So this is the logit of the probability of getting any one trial correct on average. And if I unlogit it, inverse link function, e to the logit over 1 plus e to the logit, I get 0.92. That is the mean of this variable. So on the data scale, what I am getting back is proportion correct. As one final step, it is then going to, in margins for instance, give it to me in the metric of number correct instead of proportion. So the predicted intercept from margins is 92 because that's the number of trials you got correct out of 100. So that's a little bit convoluted, but at the end of it, what you're getting predicted directly, you can think of as accuracy. You can. The probability of any one trial is functionally equivalent to the accuracy rate across the trials. Yeah, so in R then, there are more things you need to tell it. So you can have, by the way, another way that you can input data for this type of model is to have separate columns, like all your items across separate columns. I thought that was a nice feature. This option is binomial FF. I don't know why. Just because I think it was probably already taken, and so they're like, I'll put an F on it. Like, well, that's taken too. Fine, I'll put 2 Fs on it. It's like when you're trying to make a new account and you like, put in your name, like, I want my username to be Lisa Hoffman. Like, that account already exists. Like, no, it doesn't. No. Okay, I'll be Lisa Hoffman 2. Oh, nope, that one's taken too. But binomial FF for whatever reasons. So then, family function?
I think that's what it stands for.
Okay.
Binomial family function. Sorry, you piqued my interest and I needed to know.
Yeah. Binomial family function. There you go. When I first saw this, actually, I thought there was an extra A in here, and I was going to give it a whole different interpretation, like binomial as F, but that's probably not what they intended. Got to keep it clean. All right, so R agrees that here's the predicted logit that corresponds to the probability of any one trial being correct, and that translates into the same probability that we saw here. Now, this model is empty, so it's, it's about the worst thing you can do. In terms of distribution fit, though, this number right here, what do we want that number to be? Pearson chi-square over degrees of freedom? We want it to be 1. 1 means that there is as much variance in the data as what the model says there should be. Data on the top, model on the bottom is how these ratios get computed. And so this is why, by the way, Stata users, I think, Sora, we talked about this yesterday, that's why I'm using GLM in particular, as opposed to like a binomial specific routine, is because I know that this will give me this statistic. What do you know? Well, let's put some predictors in, because that could be one reason why it's too high, is because we haven't predicted anything yet. So what we're ultimately trying to characterize is the distribution that is conditional, meaning after the predictors have been included. So I added in 2 new predictors. I have grouping with respect to SLI and mother's education. And this is a dummy code centered such that 0 is NLI, not language impaired, and SLI is 1. Mother's education is centered at 12. If I forget that step, what would happen in terms of my output? What would change? We'll do a little review. What if I left off the 12 and just put it in all by itself? Would the slope for it change? Would I get a different beta 2 if I centered this variable or not? Zoomers?
There's 2 options, yes or no?
Yeah. Would I get a different slope if I forgot to center my predictor? I would not. Would I get a different slope for the other variable if I forgot to center mother's education? Nope. The reason for that is that these are not part of interaction terms. They're unconditional. How about beta 0? If I forget to center mother's education, is beta 0 the intercept going to change? Yes. Why? I liked your definitive yes.
Because, I don't know how to say that. Because you change the centering and the beta would be changed.
The beta 0 would be changed, you're right. How does centering relate to beta 0? Definition time? What's an intercept?
Predictor equals 0.
Yes, the predicted outcome when all the predictors equal 0. If you change what 0 means, beta 0's got to change right along with it. If I forget to center mother's education, beta 0 would be for a child in the not group whose mother never went to school. Pretty sure those children are not going to be in a research study, if there are such things. So yes, by the way, in your homework, one of the first things I will ask for most models is what's the -2 log likelihood? That tells you if you have the right predictors and outcome. It's like a fingerprint for your data. But the next one is what's your fixed intercept? If you get that right, I know your predictors are coded correctly. If you get the fixed intercept wrong, then something is not centered or coded in the way that I had intended. I knew that was coming. Question was, but what about if we have our own data? And there's no numbers to turn green or red and you're on your own. Well, what most people would do is pick something near the middle. That's usually a safe bet. If 0 does mean something, so for instance, if you have a variable like number of times something happened to you and something could never happen, then leave it alone. Like 0 that's the expected outcome for someone who never did this thing. I like to do not the mean, but like a nearby constant. Like in this case, I picked 12 because in the US that corresponds to a high school education. And so that's like a ready reference point. The mean for this variable in the data set is probably going to be something like 17.2. But there's nobody who wrote that down on their questionnaire. No one wrote down that they went to 17.2 years of school. So to me, it's weird as a reference point. But it doesn't change anything in terms of the fit of the model, the predictions of the model. It just changes what some of the parameters mean based on what's conditional on what. So then, the mean itself, we get number correct by the p that is being directly estimated by the model. So the logit of the probability of getting any trial correct multiplied by the number of trials gets us back to the original number correct outcome that the model is predicting. So once we put in those 2 predictors, my distribution fit is still way too high. It's 15. So this binomial by itself is not looking like it's very promising. Here's some odds ratios for effect sizes on those. So note the p-values for these, okay? Both of these predictors have p-values that are 0 to 3 decimal places in this model. Same thing in R. Here's all the decimal places that they are. I can't count that many zeros, but it's a lot. So if we try to add in extra variation to the model prediction to try to improve the fit of the distribution, there's two ways to do that. One is additive, which I went over last time, and I think I want to skip it because this way doesn't work very well. But it's the only choice that I've found if you have a multi-level model, by the way. I've never found the other alternative for more than single level data. Additive over dispersion adds in an individual level random effect. I'm going to skip ahead to model 4 with multiplicative over dispersion that we looked at last time. So this one ups the complexity by fitting what is known as a beta binomial distribution, which allows additional skewness via a kind of like a stretchy factor. So it's called a scale factor. The same idea as a negative binomial, or it has that extra k parameter. And I tried my best to notate it, and this is the closest that I got in terms of what the variance function is. It's ugly and complicated is the take-home message. But the variance is allowed to exceed the mean, but still be a function of the mean, so it's multiplicative. I had to find this. Somebody made this for Stata called BetaBin, and I had to find this in R, and I found it inside the same VGLM package, where then the notation gets even uglier. So beta binomial, no FFs though this time, and then L mu and L rho. I could not figure out what those things necessarily did, so through trial and error, I got it to work. The documentation for this package is very, very challenging to work with, but I did find it. So this time then, note that Stata does not help us figure out if this distribution fits, unfortunately. This number right here, a likelihood ratio test with a test statistic of 13, that's comparing this model to the empty model. It has nothing to do with distributions. However, if we start looking at the results, grouping still matters quite a bit. Children who are in the SLI group, do they do better or worse on this test? Children in the SLI group, that one. You vote for worse? Why is it worse? It's negative. Yes, so this is a 0, 1 variable. 0 is the N group, and 1 is the S group. And the slope tells you how the 1 group differs from the 0 group. And you have to say it that way because of the direction. So yes, the 1 group is lower because the minus sign is bringing them down. Lower by almost a full logit. Mom now has a p-value that is decidedly non-significant. So this is why we care. If you fit the wrong distribution, your conclusions will probably be incorrect. And we don't know what the right one is, but we can evaluate which ones look relatively more promising. We get some extra helpful stuff out of Stata. We get the scaling factor, which is given in 2 different versions. So it's given as 1 over this in SAS, and it's given as the log of it here. And there is another likelihood ratio test underneath it that tells us whether we need that thing. So this is directly saying, hey, is binomial good enough, or do we need this extra fancy beta binomial thing with this extra stretchy factor? What do you think? Chi-square test statistic of like 1,000. That's a decided result. So who wins? Simple or fancy? You want simple? I know, I wish it could be simple too, but no, simple lost. Yeah, because what this is asking is, do we need this additional variance-related parameter? And the fact that this test is wildly significant means, yeah, we do. And the results are quite different with it versus without it as well. But we don't know if this is good enough yet because we don't have any information about how well beta binomial fits. I can get that out of R though. I did it manually. This one. So the distribution fit index is down to 1.8. That's better than 15. But is it good enough? I don't know. What else could we add to this thing? Do you remember what we did next for counts? We were concerned about zero inflation. Let me pull the picture back up again. Do I need to be concerned about zero inflation for this outcome? No. Nobody got a zero there. But what should I be concerned about? One inflation. Yeah, that's a thing. So I go to the Google and I start looking for models with one inflation and a beta binomial, and I got nothing. And I was like, all right, I'm going to fix this. You know how I take a model that has one inflation and try to make it work for software that only has zero inflation? Yeah, my new outcome is number incorrect. Problem solved. Yeah. So in terms of my model
Lisa, does that mean the graph will be directly like changed to 1 to the 0 side?
Yep, it's all going to be reflected.
Ah, okay.
So here is a bonus points question. If I fit the version of the model that predicts, let me get back to where I was here. The version of the model that predicts number incorrect instead of number correct. Almost there. Here it is. What's going to happen to my slopes? Can I know what they're going to be? Or do I need to estimate the model to find out? Vladimir's shaking his head. Which one? Do I need to estimate the model to find out? Now, what's going to happen to my slopes if I predict number incorrect instead of number correct? Yeah. This one is going to be positive. Because if SLI children have a lower probability of getting it correct, they're going to have a higher probability of getting it incorrect. Likewise, if children with more educated mothers have a slightly higher probability of getting anything correct, then they'll have a slightly lower probability of getting something incorrect. I think I said that backwards, but you know where I'm going with this. And the reason that I can just take this and change the sign is the magic of logits. Right? If I tell you that I have a logit of 2 of getting something right, what's my logit of getting it wrong? Say it. Negative 2. Yeah. Logits are symmetric.
I thought you were going to ask me to exponentiate in my head.
No, I was.
I don't know.
A logit of 2 is like a probability of 0.9-ish, I think. E to the logit over 1 plus e to the logit. Someone can tell me. I don't have the logits memorized. That's not a thing I need in my life. But so yes, it is valid to predict number incorrect instead, and that's what I'm going to end up having to do. So to add what is now going to be 0 inflation, because I'm predicting number incorrect, what I'm doing is adding a submodel. So now I have the logit of getting any one trial wrong is still given by my linear predictor, and I have a second submodel of whether or not someone is an extra 0. More zeros than what a standard beta binomial model would predict. So in this case, I decided to go with just binomial, and then we'll try to do beta binomial. And I have an empty model for the logit of being an extra zero. Because what I want to know is, what is the probability of being an extra zero in the first place? If it's very, very tiny, that tells me I don't need to have a second submodel for this. Now, however, I'm back to binomial for the sake of building a comparison. This one does not anticipate the skewness. So it could be that I have a bad fit for binomial because of the skewness, or it could be because I have too many zeros. This will help us to try to figure out which is the problem. So I found another user-defined routine in Stata, ZIB, zero inflated binomial. And it wants to know, for your original model, what kind of link function you want. And then for your inflation model, what kind of link function you want. And so they're both logits, because I'm predicting the probability of any one trial being incorrect, and I'm predicting the probability of being an extra zero. Can you say that again? I am concerned about one inflation, to be fair, but I had to turn it into zero inflation because of how, like, my last model, my beta binomial, had a distribution fit of 1.8. So it's heading in the right direction. It's close to good, but I wanted to see if there was anything I could do to improve it. And the next choice in terms of this family would be to add something for zero inflation. I didn't understand you. Can you say that one more time? Ah. Yes, so an alternative, so the question was like, what if you have other variables? Yeah, put those in. Like, this is sort of like if you've done everything you can think of in terms of building a model and it's still not quite right, then this is something you can check. Yep. So the logit of being an extra zero corresponds to a probability of 0.41. So that's quite a bit, but then this is for the binomial model. And I have odds ratios. Here is, I found it in R, and the options are getting even weirder. So Zibinomial FF. Is that English? I really don't think so. And then we get into, I don't even know, Lone MP Struro. No idea. Not the slightest idea, but I just went digging through the options until I was like, all right, what does this do? What does this do? What does this do? And eventually I found one that did the same thing as Stata. I was like, all right, got it. I have no idea what these things mean. None whatsoever. But this is what it takes to make the model work. That's what I know. And because R sucks, look, I have two intercepts. No, I don't. One of them is the intercept for the second submodel, and you just have to know that. So this is in logits, and it's backwards. So Stata's answer for the logit of being an extra zero is negative 0.35. R's answer, even after I tried all that effort to make it work, I got 0.35. So what does it mean if it changed sign? It means R is not predicting the logit of being an extra zero. It's predicting the logit of not being an extra zero, because they're backwards. I know. All right. Then I tried one more. Beta binomial with zero inflation. The full, everything added in, like the max. And then I couldn't find it in R. So here's my note. I give up. And here's another note. I'm not even going to try to get the notation right on this. I can't. This is above my pay grade. Question? Yes, so where is that? Thank you I skipped right on over that. The Pearson chi-square over degrees of freedom from the zero inflated binomial is 13. So we really do need the beta binomial part, except that I couldn't figure out how good it is because I couldn't find it in R. So it'll just be a mystery. We just won't know. But I did find it in Stata. Zibin is what we're doing in there. And after we add the beta binomial part, the extra skewness to the distribution essentially, then we end up with a probability of 0.25 of being an extra zero. Like, oh shit, do I have to do this now? Like that's too high to ignore. So the next logical thing would be to try to predict it. So I lied. There's one more model. I put the same linear predictor in. So I'm predicting the logit of the probability of being an extra zero as a function of group and mother's education. And so here's what we have. Number incorrect is still is not related, by the way, to group, but it is related to mother's education. In the inflation model, nothing is related. And note a few things in here that should give you pause. Not just the p-values, standard errors. Yeah. The coefficient is, in logits, the standard error is 5 in logits. If you see that, you're like, oh no, it doesn't really know what that number should be. So this is, to me, a sign of model instability. I'm asking too much. And it also doesn't make any sense that grouping variable would not matter for either submodel when it's like the most important thing in the entire research study. So I don't like this one. There's the odds ratio. So here's the summary in terms of all the information that I was able to gather. So regular binomial with the two predictors did not fit well. Additive over dispersion solved the problem, but basically sent it into under dispersion because everything got moved into the upper level of it. Beta binomial seemed to be relatively best at 1.8. Zero inflated binomial without the beta part sucks. And then I used SAS to figure out what it was for the other one. So I had to add that one in here, and it is 0.87. And then I had to give up on the model with predictors because even SAS wouldn't do that. If we go with -2 log likelihood, AIC and BIC, I have a note that they may not be exactly comparable because each package is estimating things a little bit differently. But in general, these numbers are smaller is better. So the one that is the smallest should win, and that looks like it is that row right there.
All this is small is better.
Smaller is better, yes. Because AIC and BIC start with -2 log likelihood as their root, and then they add corrections for the number of parameters. Yep. Yeah, so if it's -2 log likelihood, it is shortness that you are indicating in terms of like the height of a distribution. It's not height, and smaller is better. If it's just regular log likelihood, it's height, and bigger is better. Closest to 1. So it looks like if I had to pick, it would either be regular flavor beta binomial or zero inflated flavor binomial, beta binomial, one of those two. I'm sorry? No. Yes, yeah, one of these two is what I would go with. Yep,
I think your
and here's some
question
words.
was related to like, it's okay that it's above or below 1. It's just you're trying to zero in on 1.
Yes, yeah. So if it's below 1, that's under dispersion, meaning that you're actually, like, you have less variance than what the model predicts. So your p-values would be, like, too strict in that case. Yep, and then here's the write-up. And no, you don't have a homework on this one. Okay? If you're like, I don't understand what no, I don't understand what I'm talking about either. I just wanted you to have it in your lives, okay? And if you just want to block this out and never do it again, I'm fine with that too. because this turned out to be a mess, but there you go. All right. Questions on binomials? All right then. So the rest of this is some more stuff that I have an example for. Let's see, this one. This is where we made it to. Slide 10. Maybe. There we go. One last category of generalized models, and then we change gears, folks. So the next unit is multivariate normal. We're back to normal outcomes, but multivariate. Heading into path analysis. That's where we're headed for the last few weeks of class. So one last category of that you might need generalized models for are things that are continuous or continue-ish, but still not normal due to some kind of natural boundary, skewness, or outliers. So things like response time or money. These are positive values where you can use a log link to make sure the predicted values stay positive. That means that you can exponentiate the slopes to create effect sizes. One distribution that you can use for this is called gamma. And in this, the variance is equal to the mean squared, and it does not include zero values. So if you had something to where like you had costs of something and something could cost $0, you would need to have a zero submodel for it in addition to this. And here's the one situation in which you can just transform your data. One time that I know of as an equivalence class. You can log transform your outcome. And that is equivalent to fitting a generalized model with an identity link in a log normal conditional distribution. What you would be saying is that your residuals, the log of them is distributed normally. And that works very well for things like response time that have a lot of positive skewness. And I do this trick sometimes to fix things because it's a lot easier to use standard software with a log transform. Another thing that I had wanted to present, but I still don't understand well enough to do so, is censored models. So sometimes you can end up with skewness because of an artificial boundary that was created by the limitations of your measurement. So for instance, if you are studying, let's say, recovery, all right, I'm the clinical psychologist today, I can do this. You're studying recovery after some kind of, let's go with substance abuse or other sorts of problems, and you want to know how long it takes before someone relapses. Well, if you're a really good clinical psychologist like me, your patients don't relapse, right? They're fine. So if I want to predict time to relapse, what am I going to do? I can't really like kick them out because I don't want to look bad, right? I mean, that's going to hurt my practice. So we would treat the outcome as something called truncated normal or censored. And there is a link function called a Tobit. And this is named after a person whose name is Tobin, and they called it Tobin's probit, which became Tobit for short. I can't make this stuff up. And how Tobit works is that it's trying to predict the outcome you would have had if you did not have this artificial limitation of how it was measured. Like if you could have measured these people for the rest of their lives, how long would it take for them to relapse? So my best understanding of this, and I put in a book chapter on your reading list that goes with this that is the most useful one that I found, because every other source I've seen on this just waves their hands or puts in some kind of integral that I can't understand. What it does essentially is say, okay, I understand that you have a cutoff after which you can't observe certain things, right? Like there's just like this hard line. But if the rest of the distribution is normal, then like can we sort of guess like how much should have been past the line based on what's before the line to make it like match? This is my link function gestures here. The YouTubers aren't going to get this excellent explanation. So it tries to predict a Y star that is like the pretend outcome that could have kept going. And Stata does this, and it will print margins in both the Y star can keep going metric and in the original one. And so I know there is a link function being used, but I can't figure out what it is exactly. So maybe next year. But I do think that this is useful for a lot of situations, and it could have been used actually for the test of grammar. If you think about it, a ceiling effect could have been fixed if you had more difficult items to give someone. So it's kind of like a limitation of measurement that you're seeing, one inflation in the last example. So here are some resources that you can look at if you want to learn how to do this in Stata or R to fit these censored models. I don't have something to show you, unfortunately. I can show you pictures of other stuff, though. Yes?
How do those relate to survival analyses?
So survival analysis works the same. It's based on the same idea,
Yeah.
but it's longitudinal information as opposed to cross-sectional, like you have one time to something. It's like, have you relapsed yet? Have you relapsed yet? Have you relapsed yet? And survival analysis is equivalent to a longitudinal model, like a measurement model, predicting each binary occasion with saturated mean structure. It's the same thing as a longitudinal, like multi-level model, if you predict each outcome, each occasion, as to whether or not something has happened. But then they generate these additional pieces of descriptive information about how long, like hazard curves and whatnot, as to like the people who, once they've experienced it, they're like out of the pool. So there's a lot of additional vocabulary and stuff that goes with it, but it's based on the same ideas.
Okay. I'm really glad I didn't offer to help with that, so.
Yeah, so the second half of the Singer and Willett longitudinal analysis is all about survival models, and I have that book if you're wanting to borrow it.
No, I was asked as
No.
part of the public policy consultations if I have this experience, and I was like,
No.
nope.
You kind of do, but
I kind of do,
you
but I
could
also
figure it
don't.
out. Yeah, I do believe that if you, so the biostats department would probably have classes that include survival analysis because in the medical settings, it's literally about survival analysis. So that would be probably a better resource. But it's adjacent to these things because they're censored. If nothing, like if it didn't happen.
Yep.
Right. Okay. Pictures? Since it's 3:04 and we don't have much patience for equations, but we can have pictures. Here's what gamma looks like as a distribution. It has two parameters, something called a shape and something called a scale, and I have no idea what they mean either. But I made pictures that look like this. So gamma can handle things that look relatively normal. It can also handle things that are positively skewed. And because you are predicting using a log link, the slopes would end up being this exponential type of relationship rather than linear. And here is how, at least within SAS, some of these things get operationalized. Here's a log link, or excuse me, log normal distribution. So this is designed even for even more skewness potentially. What happens is that the log of these things is normal. So the log of E is normal in these distributions. So I will show you a couple examples of that. And here's how SAS does it. SAS is the only place I found it in. I didn't find it in R or Stata. So I guess you just have to log transform your data if you want to use this one. Okay. Yes. So for these models, though, if you have something that's continuous and it has zeros, then you need two submodels because all of the log normal and the gamma are only available for positive values. So if you have zeros, then you would have to use a submodel that has the logit of being a zero and then the log of being above zero, if you're that. And I want to say on your reading list, let me make sure that I'm not talking crazy. I put stuff that I thought would be useful, and I want to say there's an article about this that in the example that I have in my head right now. 1 second. Okay, they're both K names. Let me find which one it is. Nope, that's not that one. Okay, I don't think it's on here. But there's a tutorial that I'm thinking of in my head that used this type of model for activity. So a common outcome collected from ecological momentary assessments of health and emotions and well-being is like minutes of physical activity. So this, if you put it into that context, submodel 2 would be like, hey, did you get off the couch today or not? Like, what is the logit of being a 0? Okay, I can predict that with things. And then if you got off the couch, how many minutes of activity did you get? And so within that subpopulation of non-couch potatoes, then you would predict the extent of their activity with what other predictors. So I think for these, like 0 is like a functionally different group. These are analogous to the hurdle models, but they're called two-part because the amount part is continuous rather than discrete. This is probably easiest to do using path analysis, by the way. So here's a full list of the piles of zeros terms that you would have. So if you're using discrete like counts, you can predict being an extra 0 or any 0, and that's called a zero inflation model or a hurdle model. If you're predicting amounts that are continuous, then basically all you can do is two-part with some kind of not normal continuous. There's not really a hurdle, or there's not really a zero inflated version of that. So there's the full list of things, and here's all the places you can find software for continuous outcomes. All right, 308. I want to foreshadow what's coming next, but not tell you about it yet. Okay. What do you know about data cleaning and outliers? Nothing? This is a common misconception that I see a lot. People are worried about outliers, and they do things like data cleaning to get rid of them. But you know what? Assumptions are never about data. Assumptions are always about residuals. So it makes zero sense to think about outliers if you don't have a model in which they are outlying. The question is, does your model predict them or not? But let's say that you have outliers from a model and you're not sure whether you should get rid of them. If you think back to intro stat and you first learned about central tendency measures, okay, maybe actually let's go back to 6th grade. I think this is where I initially learned these words, and you probably did too. You learned what a mean is, right? What are two other M words you would have learned at that stage to describe central tendency? Softball. They will start with M.
Medium.
Yeah, median is another one. Mode, yeah. So let's talk about median. If you have skewed data or outlier data, median is a better estimate of central tendency than mean, right? It is going to be less influenced by outliers. What's the difference? What's the difference between mean and median? What is a median?
50%.
Yeah, 50th percentile, the middleist number. If you lined up all your numbers in a row, the median is the middleist. So that means that if the highest number is a gazillion, the median is still in the middle. And if the lowest number is negative gazillion, the median is still in the middle. Whereas if you end up with positive gazillion, the mean is going to be pushed over towards it, right? So that's why median is used in a lot of contexts in which there may be skewness and or outliers, such as house prices, right? We have like the median home price because the mean is going to be biased by all the really expensive houses and people who live like in Los Angeles, New York, and that kind of like price market. Median income, same deal in terms of people earning money. So what if we could harness that technology? What if we could predict the median instead of the mean? And that way it's not going to be as sensitive to skewness or outliers. That, my friends, is quantile regression. It's not a generalized model, but it is a way to address continuous data that has skewness and or questionable outliers. And I didn't know about this until I was already on the tenure track. So I want you all to know about this. It is the same idea as regular regression that predicts the mean, but we're going to predict the median. And you know what? If I can predict the 50th percentile, can I predict the 40th? The 23rd? Yeah, I can. Yeah, you can predict any percentile. So this is very useful, I think, in real world settings. Let me get to, do I have something with that? No, I don't. It's in my head. I have words somewhere in my mind. Like if you want to know if, all right, I forgot I'm a clinician today. So I'm going to design this treatment program, and I think my treatment program is going to be more effective at helping people who are really, really low in psychological flexibility than people who are doing okay at it. So the way to operationalize that, it would be like, well, what do you mean by low? Oh, I don't know, like 25th percentile? Okay, let's predict the 25th percentile of distribution. And we can see if my treatment has a bigger effect at the 25th percentile than at the 75th percentile. Like, is X more important in predicting lower Ys or medium Ys or high Ys? We can do that with quantile regression. So, have I piqued your interest? Okay, so stay tuned for the exciting conclusion of quantile regression on Thursday. Because today is garbage day. And that means it's Thursday next. Ba-doom. All right. Any questions before we call it a day? Or things you want to chat about? No? All right, then keep plugging away on homework 4. Let me or the TAs know if you run into problems. We're happy to help. And thanks for being here. Bye, Zoomers. Bye, Roomers.
Thank you.